Hello and welcome to FlexPDE This is going to be practice problem practice for topic number 6, which is normal elasticity. So what we're going to do here is mess around with the 2018 test number 6 as the thing that we're going to solve, but we're going to add in a part of it, which is exploring how this works in FlexPDE. So let's add in a modification. Also model the beam, let's say, also model beam CD in FlexPDE and confirm the strains, let's say the dimension change and volume change. And then let's add in another modification, which is to say that we'll explore the effective stiffness. So this is, suppose that CD is restrained from moving in the lateral directions. In the, got my wires crossed there, lateral directions, which are X and Z in this case, because it's extended in Y. It goes from X is 2, Y is 0 to X is 2, Y is negative 0.8. So it has extent in Y, and we're told what the thickness out of the page is and the width in the X direction is. So suppose it's restrained and it can't actually move in those directions. And then what we're going to be asked to do is resolve parts 1 and 2 in, let's say, how about determine the effective stiffness of CD and use it to resolve parts 1 and 2 with this constraint. Okay, so that's going to be the modified problem we'll solve, which will also get us looking at things in FlexPDE and exploring how elasticity works using that tool. So let's overview the problem. We've got this member ABC, and this is rigid, the thing in teal there, and it's subjected to a downward distributed load, which is given by this formula, and this will give us something in Newton meters as long as we put X in meters. Important to specify these things. All members are light, and you can ignore their weight, so we don't have any other loads from those things. These gray triangles we'll take as the external part of the problem. So pretend these are fixed by something else that's going on that isn't seen there. Maybe a support structure there, or magic, whatever you like. Right, so members CD and CE, these things are not rigid, but are made of steel, I guess a transparent steel from Star Trek. I think it was actually transparent aluminum, but just before I get swamped in the comments there, transparent steel with a Young's modulus of 200 gigapascal, still very strong, and a Poisson's ratio of 0.4. This is much higher than steel actually has, but it's modified for this problem to make a more dramatic effect in this modification and have a rectangular cross-section that's given there. So first thing, draw an FBD for member ABC. Even if we're not asked to do this, this is a good thing to do. It's going to help us to solve the problem. Okay, so we can make some space in our paint.net and copy in this thing. It's on a new layer here, so like layer 2, which is a little bit more convenient for being able to eliminate things that we don't need in this free body diagram, like the rest of point C or the rest of this support, just the main object that we're drawing here. Okay, so now we can draw in the forces. We've got a support here, so we're going to have some reaction forces, and this is a fixed support, so we're going to have a force B in the X direction, and we're also going to have a force B in the Y direction. Sorry, I called it a fixed support. I mean, this bottom here is a fixed support, and we've got a pin, so it's not like attached to a truss or like a two-force member, so we just have so this pin can exert forces in both X and Y. It is a pin support, so it cannot exert moments. Okay, so we've got BY there, and then over here, this pin is attached to these two elements, which are two force members, right? So this thing, EC, because it has no other forces acting on it, It is not a generic frame, but a specific two-force member that therefore can only be in pure tension or compression. And that means that it just has a force up in the direction towards E if it's in tension, or negative that if it ends up being in compression. But we know that it can't exert a horizontal force. Okay, so let's just go ahead and label this force up CE and this force down CD. Totally up to you if you call it CD or DC or something, just whatever you want to call this member. I usually do it alphabetical, but sometimes I mess up my alphabetical order and call this like DC or something. But you know, whatever you want to, just pick one letter and the other letter and call this member CD. It'll be clear which member you're talking about. Okay, so member CD, member CE, there we go. So here is our free body diagram. We can copy this and put it back into the solution. Let's say solution, whoops, get rid of the red font there. Control-Shift-N, by the way, removes the formatting in Word. Alt-Shift, left arrow or right arrow, will adjust the heading level. Your headings might not look like these. I've just gone and made a template, I don't know, 14 years ago that has this style of headings and kind of liked it, so got stuck with that. You can make your own style of headings if you don't want to use Word's built-in one, and then just sort of copy it around from one version of Word to the next as time marches ever forward. Okay, so let's go ahead and start solving this problem. First thing we're going to need to do is put in the distributed load, and that is W equals 500 over x plus 1 times sine of x squared plus 1. Okay, and now we can start typing out our equations. We're going to have 3 equations from Newton's second law. The net force in x is 0, net force in y is 0, and net torque about any point we like is 0. And then we're going to have the other sets of equations, which will come from relating the geometry of this problem to figure out how the deformation of each of these beams is related, and the Hooke's law that relates their deformations to their forces. Okay, so let's start off with Newton's second law. So net force in x is 0, says bx is equal to 0. Net force in y is 0, says by plus ce minus cd minus the integral of w from x is, the bounds of this are a at x is 0 to c at x is 2. So x is 0 to 2. Okay, now we don't have enough equations. We haven't even done the torque equation, but let's see what we get. This is showing us that we've got 2 arbitrary parameters still in there, CD and CE. But another thing that's interesting is the answers are all in terms of these like psi of 2 and other psi with a C, lousy English, psi of 2 as well, and psi of 6 and psi of 6, I don't know, chi of 6 maybe? C of 6? Oh, they both would be C. This is, yeah, again, English's fault. Now this is just telling us, these are functions that are the integrals of sinc functions, of sine of something over something else, where, you know, a sinc function is if you have sine of x over x. So if you take the integral of that, that's the special name that we're talking about here with these psi functions. Basically what Maple is doing here is it's saying, I don't need to introduce numeric error by evaluating exactly what this function is, even though it's perfectly well behaved of a function. It has a strange name there that you may not be familiar with, but it's just a name for the integral of sine of x over x, and that showed up because of the form of the w that we had there. So what we could do is, if we wanted to force it to evaluate that, we could just take the range into turn the range into a floating point number, and then Maple say, well, okay, we're stuck with floating points, so I'll just tell you the value of those integrals. There still is an issue where we don't have enough equations to solve for the unknowns, but at least now we're getting the numeric answer and don't have to guess at what the integrals of these sine and cos functions are. All right, so let's go and write that torque equation. How about point B? Relative to point B, the net torque provided by Bx and By is 0. The torque provided by CE and CD, let's say out of the page, we've got 1 times CE minus 1 times CD, and then we've got the torque produced by W. And at any point x, the displacement that we have would be integral of x minus 1, that's the displacement to the right, times W, would give us a torque into the page. So we can say times negative W from x is 0 to 2. So this integrates over the whole object. We'll put a comma here to separate those lines out. Integrates from x is 0 to x is 2, adding all of that up. And at every point where x is, we've subtracted off the coordinates of this point that we're finding the torque about in order to do this integral. I deliberately did this about a point where we would have something non-trivial there. One, because it actually is a good point for eliminating b, but two, to point out that it's not always just the integral of x times w. We've got to be really careful about how we set up these integrals to make sure that we're going to be calculating the torque correctly for these distributed loads. So now we should have one less parameter still in the answer because the torque equation is not going to be redundant with the net force and y equation. Let's see. Okay, it's a little bit hard to see with these integral functions sticking around, so let's convert those to floating points. And yeah, just one unknown parameter, which we can clean up by doing the stuff from this week. So what is that stuff? Well, we've got some elastic modulus, EY is equal to 200E9, and some Poisson's ratio, which I guess actually we're not going to need at the beginning, but we will need some cross-sectional area. Area is equal to 1 centimeter out of the page and 5 centimeters in the x direction. So the area is equal to 0.01 times 0.05 in meters. And then what we have is the ability to, well, let's see. So here's the idea. The force that we're going to be putting on these things, the CD and CE, let's just take CD, for instance. The amount that this pulls by, CD, divided by the area is going to be the stress, right? So maybe we can give a name to that. You could just put this all in one equation, but it might be more clear if we give a name to that. So let's say sigma CD is equal to that. So we define the stress. And now we can also define the strain. Epsilon CD, this is the strain in the y direction. Maybe, I suppose we could call this sigma y CD. Epsilon y CD, what would that be? What's the strain? It's the amount that this point moves up, which is, let's say VC, because it's a displacement in the y direction. So, and that's going to match the syntax we're using in FlexPDE. U is the displacement in x, V is displacement in y, and W is displacement in z. So V at point C. What else? So that's the displacement, and that's like the change in length, right? Because the other end of it is fixed, point D doesn't move, then the change in length is just how much point C moves up. And to get the strain, we just divide that by the original length of this, which is 0.8. Okay, so we've got VC over 0.8, and that's our strain. So now we've got the stress in terms of the force, and we've got the strain in terms of the displacement of point C. And the next thing we need is Hooke's law. So Hooke's law will tell us how the stress and strain in this material are related. And that is that sigma y CD is equal to EY times epsilon CD. All right. Now this is not going to really solve stuff either, because here what we've done is we've introduced 3 new equations, yes, but each one of them introduced a new unknown. So before this equation, we didn't have sigma y CD. Before this equation, this equation actually introduced 2 new unknowns. We have epsilon y CD and VC, which we didn't know. And then this one didn't introduce any. This one just is in terms of the previous ones. So actually, I suppose if we put them in this order, then it's fair to say that each one introduced a new equation and also a new unknown. So we've got this stress related to the force, and then we related the stress to the strain through Hooke's law, and then we related the strain to the displacement of point C. So far, this hasn't helped. But if we do the same thing for CE, we can write that in terms of this same displacement. And so the first two equations will again introduce one new unknown each, which won't help, but the third one will introduce no new unknowns because we already have VC introduced into this, and that's what's going to bring it to a close and let us solve. Try that out on your own if you can. Here's the answer to that. So we're going to say, again, sigma in the y direction for CE, sigma y CE, the stress is going to be equal to the Young's modulus times epsilon CE, except this time epsilon CE is not related to VC, the upward displacement of point C. It would be actually related to downward displacement of point C. So that's negative VC. Why is that? Because we're going to have a tensile strain in member CE if point C moves down, right? The other end of it is fixed at point E, so the amount that this moves down is going to be determining the tensile strain. So VC divided by the original length of CE, which looks like is 1.2. So because it's longer, the same amount of displacement will not create as much strain in this thing, and that's why it's going to have an effectively lower spring constant. Finally, epsilon, we can relate the strain to the stress, just like we did for the other material, for the other bar. Epsilon CE is related to sigma y CE. I guess we want to call this epsilon y. Yeah, make sure we've got the same variable names. Epsilon, yeah, sure. Epsilon CE, and that's related to sigma CE by the stiffness. Oh, you know what one we're actually missing? We did put in the Hooke's law. What we didn't do is put in the stress related to the force. Sigma y CE is equal to CE over the area. It's the same area. All right. So then, if we haven't made any mistakes, this should be everything. We've got our Newton's second law. We've got our Hooke's law and definitions of stress and strain for CD, and then same thing for CE, where we've also written the strains in terms of the motion of point C. Okay, so it didn't work, but I can see right away that I didn't write one of the variables correctly. I wrote it as just epsilon, and there it is. So it's supposed to be epsilon y. Okay, now it looks like everything is solved. Let's explore this. So we've got a force in the y direction at B, which is 849, and CE is actually very small. It looks like this one is compressive, so that means CD definitely has to be tensile. It is, and not very much. So that the fact that BY is most of everything here means that we've got most of the force just supported by this pin, right? So this pin is dealing with almost everything in this distributed load, right? The distributed load leading to the force here is pushing all of the response to this over into this pin. How could we get most of the response to be over in these two bars instead? Well, we could change the function so that it is centered not around this point, but around one of the ends. So this must mean that W is mostly around point 1. Let's have a plot of W and just see if that's the case. Does W have a peak at 1? Not really. It's actually a lot more over on the left. So that means there's something a little bit fishy about this solution right now. You know what? I've been confused by the scale. So I got bamboozled. This is going to, this is not going all the way to 0. If we were to plot this in a way that also had maybe force or like distributed load df equals 0 to 500. Plot this on this scale, you can see actually the distributed load is pretty much uniform, and because B is in the middle, that's why it takes up most of the load, most of the weight there. If we were to change the distributed load to one that is a lot more at the left, maybe, or a lot more at the right, then this would be doing something that is, then we would expect to have a lot more force over here compared to B. So let's imagine we take this and we multiply it by x squared. This is going to multiply it by a parabola, right? Now we've got a force that is a lot more over on the right, and consequently, we have By not needing to be as strong compared to the other things, right? CE and CD have increased quite a lot compared to what By did. If you multiply this by a larger thing, like maybe x to the 4, then we would expect most of the force to be not By, but now CD and CE. So yeah, together those are now larger than what By was doing. Furthermore, when we put most of the force over here on the right, then we have the strain in CD being compressive. It's pushed down here, and CE being tensile. So you see this is a tensile stress and a tensile strain. It's extended by this small amount, small fractional amount of its original length, and the and CD has compressed. So we have a compressive stress being negative and a compressive strain as well associated with that compressive stress. All right, so let's return W to the original form where we don't have this multiplying by x to the 4 thing, and that's going to make the force a little bit higher on the left. So now we have the opposite. With the force a little bit higher over here, that means CD is actually in tension and CE is going to be slightly in compression. And indeed, that's what we find. So CE now has a slight compressive strain and compressive stress, while CD has a slight tensile strain, less than before, and associated tensile stress. To find out the next thing, the equilibrium displacement of point A, we can notice that the distance from B to C is the same as the distance from A to B. So that means in this particular case, the amount that A has moved is going to be equal to negative the amount that C has moved. So VA, we can assign this and then say VA is equal to negative VC. The vertical displacement of A is equal to negative vertical displacement of C. So there we go. So here's the equilibrium displacement of point A. It has moved down by 0.16 microns. So next the question asks us to create an internal shear force and bending moment diagram for ABC and to include a free body diagram showing the split that we used to define the internal shear force and bending moment directions. So we'll go back over to here and we can split this anywhere, cut and paste it, and then show the directions. Now it didn't actually ask for the internal normal force, it just said internal shear force and bending moment, but for good measure, we can add that in as well as a bit of a bonus. So there's the normal force. We'll take the shear force and draw it using our standard sign convention. And the bending moment, get like a purple color for that because we haven't used that one yet. There's the moment there, and over here as well, same moment on the other side. Okay, so there we go. Newton's third law action-reaction pairs for all three. There is the split that we used. Maybe to put in the solution, we'll call this the split. So this is 1A FBD, and we'll call this 1C FBD. All right, next up, we can go and write out what those internal forces and moments have to be. So forget about this plot. We can write the normal force as we move along. That's just actually equal to 0 this whole time, so maybe forget that, because bx is actually just equal to 0. But if we like, we could put piecewise if x is greater than 1, that's where point B is, then we will have negative bx. And this looks like it won't balance because that's the only force. We'll be adding a force partway along, but bx is just 0, so that's what makes this work. Okay, next up, the shear force, V, is going to be equal to negative the integral of W from x is 0 to x. Because as we add up that W force down, the more W we have to counteract with V. V is going to end up being more and more negative to counter that. Plus a jump of By as long as we're past x is 1. And then that'll take us all the way to the end of the thing. But just to add that in and see that we go back to 0, we'll say plus piecewise if x is greater than 2. Let's see, we will increase the shear force by CE and decrease it by CD. So let's see how that looks. Just go slightly past the end. And it does look like we have jumped down by the small amount that we have for the value of these forces at the end. The reason it's not much of a jump is because CE and CD are not very large here. Just for fun, let's go back and put this modification to the force back in. And now with most of the force over on the right, you can see there's almost nothing going on left. And then we jump up by the big force By that has to counter a lot of these, but not nearly as much as the jump up at the end that's counteracting where the bulk of the force is. Okay, so we'll take that out and figure out the moment. To deal with the moment, we're going to go with m is equal to the integral of V because we assigned it in this direction so that the moment is just the raw integral of V from 0 to x. And we don't have any point moments to add in, so that's actually the end of it this time. We can plot this as well, even though they're in different units, if we remember that they are in those different units. So yeah, we've got the moment being that the shear force is the slope of the moment. It starts off at 0, no point moments applied there. Having this kind of quadratic opening down, and then quadratic back up as we jump up to a positive force, but with the thing kind of decreasing down as we move along. It's not quite quadratic because this is not quite a straight line because W is not quite constant. So that's what's leading to this shape. But because W is mostly constant, the shear force ends up being mostly linear, then a big jump at B, and then mostly linear until we have this other jump there at the end. The moment has to end up at 0 though, because unlike the point loads that we have applied by CE and CD, we don't have a point moment at the end. So that makes sense that it returns to 0 there. Okay, so that seems all good. What about when we add in this more complicated thing and there's a lot more force over on the right? Same thing for the moment. The moment will end up being basically 0 until we have a really large force applied there, and then the moment will change and change back. Let's see. It's probably what's going to be happening. Yeah, so moment basically 0, jumping up, and then after the shear force becomes negative, moment curves around and goes the other way back down to 0. All right, so let's get rid of that just before we forget and go back to the original problem and then continue on with the next part. So next part is determine the stiffness and compliance matrices for the steel of member CD. And the matrices themselves don't depend anything on the geometry, so we don't need to know about the dimensions of this to figure out these matrices. To get those, what we can do is jump back to the notes and go to the part on stiffness and compliance matrices, and then copy in the code that has this already written out, and that's probably the easiest way. So we'll take this code, go over to our maple section here, and we can put in these generic ones, or better yet, we can put in that E is equal to 200E9 and new is equal to 0.4, which were the things given in the start of this problem, and then work out exactly what the stiffness and compliance matrices are. Remember that this one is the stiffness matrix and this one is the compliance matrix. Okay, so there we go. If it looks like this, that just means that we don't have a large enough screen to show the matrices as matrices. There's a lot of decimals here. If you mess around with Maple's display precision, then you can have it round to a different number of digits, because this is clearly not quite right. There's too many decimals in this. Another thing to do is you can remove the floating point numbers by making this 4/10 maybe. Nope, we also need this to end up as an integer. So maybe the 200E9, maybe 200 times 10 to the power of 9. Yeah, okay. So now we've got it not evaluated as a floating point, and this might be easier. It's perhaps even harder to read because of these fractions that it's left us with. Yeah, perhaps if we now, I wonder what happens if we now convert this to a floating point. Whoops. Don't suppress that output. Let's see. Okay, so this is a little bit nicer because it's gotten rid of some of those rounding things. Leave it without rounding until the very end. Right, so maybe a little bit nicer. We don't have to have the screen quite as wide to be able to display these. And this is done by forcing it to leave things as integers until we get right to the end, and then expressing it as a floating point. Next up is to calculate the change in dimensions of member CD and assume the stress in each dimension is uniform in order to do this. So we're going to ignore edge effects from the pins and say that the stress that we needed in CD is the stress in the Y direction. That was a Y-directed stress. Say that stress is the stress everywhere in that object. Okay, so we can do this by keeping in mind how the stiffness and compliance matrices work. So the stiffness and compliance matrix tell us how the stress and strain are related. The compliance matrix, when you multiply it by the stress, will give you the strain. So we can say that epsilon, which is epsilon x, epsilon y, epsilon z, and sigma, which is sigma x, sigma y, sigma z, are related via the compliance matrix by writing out that epsilon is equal to s dotted with sigma. Okay, and for the particular compliance matrix that we have for this Young's modulus and this Poisson's ratio, we end up with the following relationship. So in the case of this particular problem, what we can do is take all of this, put it after these things, and then write out, I wonder, we've got E assigned there. We did assign both E and EY earlier, and they mean the same thing. So that could get a little bit complicated, but I think we're okay if we're careful. Maybe you're looking back from the future after I already made a mistake by mixing those up, and this sounds kind of ironic. But anyway, for now, I think we're okay. We haven't made that mistake yet. So the strain is equal to the compliance matrix times the stress vector. And what we can say is that the stress, in this particular case, is Sy, is equal to the stress that we found in this last example, which is sigma y CD. Sigma y CD. Okay? So that's the stress in member CD in the y direction. And the other stresses, Sx is 0 and Sz is equal to 0 because it's not constrained in those dimensions, at least not until the modification we're going to do in part 3. So then, what we have is the strain is equal to this. And as a check, this should be reproducing the strain that we found in the y direction for this particular beam because we put in the same Young's modulus. That one only depended on the 200E9 once we know the stress. So sigma y CD is uniquely determining what epsilon y CD should be via the Young's modulus. And indeed, that is the same thing. And we've got a smaller one that's equal in the other two dimensions, right? So through the Poisson's ratio, negative Poisson's ratio times this will give you what the strain is in the other two dimensions. So that's the strains, but that's not quite the change in dimensions. To find the change in dimensions, we're going to need to multiply each of these strains by the dimension that the beam had in X, Y, and Z. Okay, so we can form the dimensions original vector by going and putting in the dimensions. It was 5 centimeters wide in X, 1 centimeter in Z, and the 80 centimeters that it was in Y. So let's put that in. Dimensions original is 0.05, 0.8, and 0.01. So here is the list of original dimensions of this thing. Maybe to mess around with this for a little bit, let's go and make a new thing there. Okay, so here's our dimensions. And what we're going to do is then modify this by the strain. So dimensions new we will get by taking the original dimensions and then adding 1 plus the strain for each of them. So we could take dimensions original 1 multiplied by 1 plus epsilon 1, right? And then add this and then do that for the other ones as well. But we may as well use a sequence if this is what we're going to do. So let's do a dimensions original n. Yes, from n is 1 to 3. So that should do it with a semicolon. Okay, so there we go. Oh, we didn't assign the epsilons yet. So we need to do that as well. And this is a little bit tricky because we just sort of had that epsilon is this, and we've got another thing here, which is that the strains are equal to the right-hand side of that thing. So what we can do is actually just assign, well, okay, hold on. Maybe let's go and look at what we're looking at here for a moment. So we've got this, and we want to assign the left side terms are equal to the right side terms. In general, we might want to actually sort of solve each part of this. So let's make this like the strain equation, and then what we can do is solve that so we want to extract each of these as a list. So first of all, let's check this out. Strain equation 1 will not work because the whole equation cannot be subscripted. Let's get rid of this to see what we're doing here. But what we could do is left-hand side it. Left-hand side the strain equation, and now left-hand side extracts just this part. 1 of that gives us that. So here's what we want to do. We want to go strain equation left-hand side n equals strain equations right-hand side n. Okay? This doesn't let us do anything, but if we sequence this, then we get all 3 equations out. The first equation, second equation, third equation, and then we can solve it. Well, in theory. If we, yeah, I know what went wrong. We assigned each of these as different arguments to solve. So we gave it the first argument is this, but solve expects its first argument to be a list of equations. So we just need to put these in lists. That's what solve is, that's what this error is trying to tell us. Okay, so if we put that in a list, there we go, we solved it, and now we've got a thing that we can assign. We could have just assigned it right from these equations, but if we had something more complicated here, then this would have been a more safe approach by first asking it to solve that and then assigning that result. Once we've assigned it, this will no longer be runnable again because now we know what EX is right from the start and there's nothing to solve. So the output is a little bit funky afterwards. Anyway, once we've got this code executed, then this code is going to be able to figure out the new dimensions by adding the new epsilon. Okay, so now we've got the original dimensions, we've got the new dimensions. The new dimensions are almost the same because there's almost no change in the in the dimensions because the strain is so little. So how do we find out the volume change? Well, we would have to find out the volume new by multiplying each of these three different things. And this we could do with the product function, but unfortunately the product cannot take a vector as its argument. It first needs this to be converted into a list, and this is kind of obnoxious. So what we need to do is sequence this thing, n equals 1 to 3, and then make a list out of that result, and now we've got something that we can product when we subscript it. Yeah. So just as a check, this did actually go and multiply these three things together. If we take 0.05 times 0.8 times 0.01, then we should get exactly the same thing. Yeah. Now, I called this volume new, unfortunately, because this is actually the original one. But we can get the new volume by doing the same thing, but with the new dimensions. Okay, so the new volume is almost the same as the original volume because the new dimensions were almost the same as the original dimensions. And so all we need to do to find the change in volume is subtract them. And there we go. Volume change is incredibly small, 0.16 times 10 to the negative 10 cubic meters. All right, now we're ready to put this into FlexPDE and check the dimension change and volume change. Here we go. So we've got our FlexPDE code, very similar to the one in the notes, but named slightly differently. 2018 test 6 mod. Okay. And what are we going to do? We're going to put in the dimensions that we want. So I've gone and written those in already. 5 across in X, 80 centimeters in Y, and only 1 centimeter in Z. Quite a lot of aspect ratio. So we might have trouble doing this in FlexPDE, but let's give it a shot. We've got a Poisson's ratio of 0.4. E is 200 E9. And I think that is it. I don't think we need to change. Oh, we need to change the stress. Right. So what do we have? We have a load on the positive and negative Y faces. So when Y equals 0, we'll say that there's no displacement there. Value of V is equal to 0, and we'll leave everything else the same. So we'll put no condition in for U or W will be defaulting to the default no stress in X and Z. Okay, so with no Y displacement on the bottom surface, and then on the side, on the X equals 1 side, what's going on is we start off at the bottom, draw this for X. First we change, so imagine like this is our 0, 0 in FlexPDE, and then we go across to LX0, which means we go across to here, and then we go up to there, and then over to there, and then down to there. Yeah. So we've got this moving across to from 0, 0 to LX0, and along that bottom line, we want to say there's no Y displacement. Then as we move up the side, we want to say that there's no force in the y direction. Load V is equal to 0. No stress in y on this side. Not x equals 1, but x equals Lx. And then we're along the top, along y equals Ly. And on this surface, we're going to say that there's a load in the y direction, which is going to be the stress that we have in y. And we've figured out that the stress that we have in y up at the top here happens to be equal to the sigma CD, which is 40,000. So we've got a stress of 40,000 tensile on the top surface. And then along the x equals 0 surface, which is the left side of this, going back down along the left, we want to have no load in y again. Load V equals 0. So the 4 boundary conditions that we're setting no y displacement on the bottom, no stress in y along the side, no a positive tensile stress in y of 40 kilonewtons per meter squared, 40 kilopascals along the top, and then no stress in y along the left side as well. And that's what's going on in this beam. So, yeah. Now here, rather than 0.5, let's say 0.5 times Lx, 0.5 times Ly, and 0.5 times Lz, so that we get something that is inside of the material for evaluating these strains. And let's just check that this actually runs for now. Okay. And the strains that we got look familiar. Are those the same strains that we had in Maple? Yes, looks the same. Okay, so far so good. Now, figuring out the volume change is a little bit more involved. For this, what we're going to want to do is find out what the displacement is at the top right corner and then subtract the displacement at the origin. So report val of u at Lx, Ly, Lz. This will be telling us what u is at the very top right corner. Now that's not the change, that's the change in position at the top right corner. To find out what the change in length is, we need to subtract what u is at the other side. So if the other corner is holding still, then we can use, like if it's not rotating or anything, then we can use this as a way to find out. So the right side moves somewhat, and the opposite corner didn't move differently in x. Because we didn't fix any of the sides in x, one side moves by a certain amount, the other side moves by another amount, and really the change in length is the difference between how much these different sides moved. I suppose really what we should do is do this at different y and z values, but yeah, well, actually it looks like that does even make it does actually make a difference. So along one side, what is the change in the x position versus on the other side, right? So when x equals 0, we have a certain displacement, and when x equals Lx, we've got another displacement. So it looks like this whole beam is in fact kind of rotating a bit. So maybe we need to set some more boundary conditions to figure out how this thing is actually deforming. So a way to do that is to find a surface where x is equal to 0 and just pretend that that is not allowed to move in the x direction. So let's do that. Let's take a surface where x equals 0, which is this one, and suddenly set that the value of u is equal to 0. And now we've got it nice and fixed so that on this whole bottom surface, it doesn't move. Notice we didn't actually change the other values, right? We just, I think actually we made them closer to what we would have thought. Yeah, there's actually less round-off error by helping the program out and saying, you know what, x is not allowed to move. It's not allowed to move in the x direction. No displacement in the x direction along the x equals 0 surface. And then the other one, now the opposite side, will tell us exactly the displacement of that surface, which now is the length change as well. So this displacement of this surface is now also the length change, and the new length would be the original length plus this displacement. Let's see. It is basically 0 with the display precision that we have here, because it's only for E minus 9 is the displacement there. Is that right? So the strains multiplied by the dimension. Yeah, okay. So the new dimension is pretty much identical if we round off to this many decimal places. We've got 4 times 10 to the negative 9 in the negative direction for x. So that is not really changed that much. Okay. So let's see. We can calculate what the volume change is. Considering all of this, we can take these expressions, and rather than writing them out down here, we can write them out in the definition section. Anything that we kind of want to use later. Rather than reporting it, we'll say that Lx new is equal to this. Ly new is equal to value of Ly plus V at that corner, and Lz new is equal to the value of Lz plus W at Lx, Ly, and Lz. And then we'll say volume new is equal to Lx times Lx new times Ly new times Lz new, and vol change is equal to vol new minus Lx, Ly, Lz. And we can report that. Report vol change. Let's see. Do we have the precision to calculate this? It looks like we do, but it is not exactly equal to what we found in Maple. It's on the same order, but not quite exactly the same. Let's see if we can clarify this. What's going on in Z? Well, we can do something similar here and report what W is at the opposite corner. So here's sort of an issue. The thing is rotating around a little bit in Z, and it's possible that it seems likely that our W difference there from one side to the other is not quite doing justice to what we would have hoped. So with it rotating around, then we can't just take Lz plus W at the far corner and say that that's the new length in the Z direction, unless we also have gone on the Z equals 0 surface and said you're not allowed to move in Z on that surface. Now, actually, this is not the boundary condition thing. I did that in the notes video as well. This is the surface where we can set that there's no Z displacement. And that one, I think, works just by setting one of them. You don't need to set the other one. So now we do have a W displacement, which is working. At 0, there's no displacement. See this E minus 26? That's showing us what the precision of FlexPDE is in this example. And at the opposite corner, we're getting to E minus 10. That's our displacement. Where's that one? This one here. That's the displacement in Z of the far corner. That's the change in the Z length. So if we add that to the original Lz, we'll have this thing. So this is showing us the change right there. So it looks like the change is 8 times 10 to the negative, how many are we over here? 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I do that right? 10 to the negative 8 times 10 to the negative 10? Yeah, seems right. Okay, that agrees with what we've got in Flex. And now it's agreeing with the volume change. So the thing that made the difference again was by setting that the displacement in Z is 0 all along the Z equals 0 surface. Once we've done that, the new since that surface isn't moving in Z, the opposite surface at Z equals LZ, just by using the opposite corner, but we could have used any point on that corner. Let's just use maybe Ly over 2 and Lx times 0.2. This is just some other random point on that same surface. It shouldn't make a difference. And yeah, we've got exactly the same total volume change now. By setting the Z equals 0 surface, the bottom surface, to have no displacement in Z, now when we just take what the Z displacement is at any point on the opposite Z surface, that'll be the length change in Z, right? The displacement on the other side, if the Z equals 0 side isn't allowed to move, will now be the length change in Z. Okay, so now we're ready for modification 3. Suppose that CD is restrained from moving in the lateral directions in X and Z. Find the effective stiffness of CD in the longitudinal direction and use it to resolve parts 1 and 2 with this constraint. So what we're going to do first, there's a bunch of different ways that we could do this. One way is to go back over to the notes. Oh, by the way, in the notes, remember that you can't use just this method to find the fractional volume change because this was for a cube. So you can't just take L cubed multiplied by the sum of the strains, because what L do you even use, right? So it's not quite this if you're not dealing with a cube. Okay, anyway, the effective stiffness is talked about in this section. And so if you have two axes fixed, we figured out that the effective stiffness that you use is actually this thing, which is a fair bit higher if the Poisson's ratio is higher. So it looks like we should have an effective stiffness for the for beam CD, which is larger by this amount here. So if we take CD and we multiply it by this thing, this should give us the new stress that shows up. Like we have an effective Young's modulus that's that much higher in the length direction by having it fixed in the other directions. So this should tell us what the new results are. How does this change things? We'd expect that it doesn't move quite as much over here if CD is stiffer, right? So this will resist motion a little bit. It doesn't change how much of the force has to be over here, but it does change how much the thing is allowed to move up and down. So what do we notice? We notice that By is the same as it was before, I believe. Let's compare this to these earlier results. So yeah, By is the same. Actually, the stresses are not quite the same. So CE looks like it's actually lower and CD is higher. Why would that be? Well, the change in the stiffness of CD stops it from moving as much, but we didn't change anything about CE. So if it moves less than it did before, right, having this 0.948 E minus 7 instead of, where is it here, 0.16 E minus 6. So we've moved a fair bit less than before, not quite half as much. So 0.94 instead of 1.6, but we've moved a fair bit less. And this means with the stiffness of CE not changing, that the stress CE and the force that it's putting out has to be a lot lower, like almost half as much as it was earlier. CD, though, has to take up the rest of it. So the same amount that this reduced by, this has to increase by to have all of the rest of the static stuff be the same. So that's the effect of having one of the axes or both of the axes fixed for CD as far as the statics go. It doesn't change anything about the shear force and bending moment diagram because we have the same total force over there. With less displacement, we're going to have less strains in X, Y, and Z for this object. We can now go and execute the next part. And let's make sure we're on the same page here, that everything's working. We need to change. Do we need to change the effective stiffness? No. Well, we don't. Sorry, this isn't the effective stiffness. In this part, when we're putting it into the matrix, this is the actual Young's modulus, and this is not changed. All that's changed is the apparent Young's modulus from the perspective of the using this thing as a spring, because the other dimensions are not allowed to move. So in Maple, we can get this worked out by now setting, instead of the stresses are equal to 0, instead what we're going to do is set these strains in X and Z equal to 0 and apply the same stress that we did vertically before and see how this works out. So here's exactly why it's useful to have the raw equation form written out, because now it's okay that we had the stresses in Z and X unknown rather than the strains. By going in and using this method where we just wrote out the 3 different equations and asked it to solve, we can still solve for exactly those 3 unknowns and then use this information to find the new dimensions and the volume change all the same. So the fractional volume change is likely less than it was before. Let's see how that works out. Aha! So this is actually more volume change than it was before. Why does that make sense? Well, we are stretching it out in the y direction, and even though it didn't move as much as it did last time, so if we, let's see. I wonder how we can compare to the last one. Oh, you know what? We could have this FlexPDE report the displacement at the top. So let's say value of Ly plus V at the other end. Yes. Oh, wait. We are losing the precision that we need there. Let's have just V. See how much the displacement is at the other end. So previously to fixing the sides, we ended up with a displacement on the other end, which is 1.6 e minus 7. And now what do we have? We have got 9.52 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8. So if I did that right, 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8. 9.52 times 10 to the negative 8. Before, we had 1.6 times 10 to the negative 7. Yeah, so we had almost double the displacement in y before. But before, we had a reduction, a counteracting displacement in x and z, and now we've prevented that from happening. So even though we have less displacement in y, the actual volume change is higher. We've got a larger amount of, we've got more increase in volume compared to what we had before because we haven't allowed it to compress in on the sides. To confirm this in FlexPDE, what we need to do is take the stress that we calculated, this sigma CD, which is 50.816, and apply that instead. So 50.816, and then change the boundary conditions on the sides from, instead of being free on the other side, to being fixed. Value W equals 0 on the top surface, no Z displacement on the top, which is like really the front in the way we're drawing this, and no X displacement on the other X surface. But after we set this, to remove that boundary condition on the surface in between, we have to say the load of U is equal to 0. Okay, so this should now be reproducing, if we haven't made any mistakes, the volume change that we had before and the new displacement in the y direction. And it looks like we've got it. So just to look back over this problem, what we did is started with this setup, drew a free body diagram for this beam, and then related the force in each of these beams to the displacement of this point and their elastic constants, their effective spring constants, which we determine from the stiffness of the beams and their cross-sectional area and their lengths and their material. I guess the stiffness as their material property. So using all of that, we were able to figure out what this displacement was and what this displacement was, what all the forces were. Then we created an internal shear force and bending moment diagram to look at how this looked across the thing, and then did some work on this beam CD, just exploring a little bit more about it. Found its stiffness and compliance matrices, found out what the changes in its dimensions were by working out what the strains were in the 3 dimensions, and then taking 1 plus the strain times the original dimension to find the new dimensions, and then worked out the volume change by multiplying those new dimensions and subtracting the product of the original dimensions. Then we did this in FlexPDE as well by setting up boundary conditions on the bottom of holding still in Y and on the top of moving in, of having this stress that we found out from the first part of the problem in Y, and said that it can't move in X on the X equals 0 surface and can't move in Z on the Z equals 0 surface to more easily figure out what the total new lengths were, new dimensions were of this object, and then find out the volume change. Then we used the analytical result for what the effective stiffness should be if you have 2 axes fixed on this object, given its Poisson's ratio, to redo the first part of the problem with a different effective stiffness for CD. Used that information to find out what the new stress would be on this object, and then analytically calculated what the new volume change would be, and confirmed that with FlexPDE by applying that new stress directly and fixing both the close and far side in X and the close and far side in Z. Thanks for watching. I'll see you next time.